Hello, my name is Andrew Choi, and what you're looking at right now is a project I've been working on for quite some time. It is a graphics renderer, which is a computer program that draws an image from a bunch of data that you feed it, usually about an object or a location. I've worked on this for a few years. It's gone through several iterations, and I had to research quite a lot about it, usually things like data structures and actual ray traversal algorithms. A lot of things have been discarded over the years, but for the most part, I think it's in a showcaseable state where I'm confident enough to talk about how the actual engine works and really showcase all of the visuals it's able to produce. If you're meaning to just look at the visuals of the video and are not interested in learning about the technicalities of how the engine works, you are free to skip towards the end of the video or just all throughout the video to see the visuals. Right now, I will be explaining the theory, implementation, and future of the engine, along with the limitations and things I want to get done in the near future. Before we can talk about how my actual engine works, it probably would help to first understand how real-time modern graphics engines actually render their images. Modern graphics engines usually use something called rasterization. Rasterization is an algorithm that projects geometric primitives, usually triangles, onto a screen or image to give the illusion of 3D positioning and depth. This has its pros and cons, but modern hardware has gotten to the point where it can project millions upon millions of triangles around 60 times a second, which is more than enough for most applications. My engine actually does not use rasterization. It uses an alternate technique called raycasting. Raycasting is a technique that performs rendering by intersecting rays with objects in a scene and uses information from the intersection to render the actual pixels on the screen. These intersections can actually be sped up with a technique called ray marching. Ray marching is a technique that samples data along the path of a ray for doing things like querying how distant the ray is from the nearest object and stepping the ray along those distances. To perform these samples, my engine uses a data structure called voxels. Voxels are units of data that are organized in a 3D grid-like structure. Think of them as volumetric pixels. They can also be used to actually describe the scene that the renderer is rendering. In my case, the voxels used in my engine are used to describe individual cubes of a given color. The position of this voxel in the grid corresponds to the actual positioning of the cube in the scene. They can also be used as a structure to define which spaces in the scene are actually empty. If the ray is currently traversing through an empty area as indicated by, say, a volume in the grid that is empty, then the ray can just simply skip that space, saving a lot of performance. My engine implements voxels by allocating memory on both the CPU side and GPU side of my computer. The memory itself is divided into 32 by 32 by 32 chunks of 2-byte data. The voxel in each chunk can be used as a pointer to another chunk or just as a value in itself that can be interpreted as a color. This allows the chunks to act as a sort of node in a tree data structure, although incredibly unconventional seeing how it's not very sparse with its 32 cubed data and also the fact that it only goes down 2 levels. On the CPU side, these partitions are organized into an array, but on the GPU side, it is organized into a 1024 by H by 1024 3D image texture, where H is a number that is calculated at the start of the application. Memory is then synced between the graphics card and the CPU, where the CPU generates the chunks and the GPU receives them. Additionally, each chunk on the GPU has a corresponding volumetric chunk that has several MIP levels that can be used to sample distances within the ray traversal. The advantage of having this hierarchical voxel structure is that chunks can actually be reused even when the map is itself moved. The engine just reuses the chunks in different locations within the top level hierarchy, as shown in the video right now. Interestingly, the engine actually searches for the chunks most nearest to the actual source position. So even though that the actual world position of the chunks is changing, the engine tries to maintain the illusion that the world itself is still there around the user. The engine itself is far from finished. I still have a lot of plans going forward. For one, there is no way to actually edit the individual blocks within the partition. For instance, I am not able to place down another brick within the map. The engine is very much capable of doing that, but there is no hard-coded method of doing it at this time. There's also no streaming implementation, so what happens is that chunks are generated and they are discarded and are never actually used again. Of course, saving to disk and then streaming from there would be a more optimal solution. The chunk generation itself is not the most prettiest or even the most efficient. It is just right now using 3D simplex noise. Going forward, I would like to change it to a more visually pleasing terrain generation with much more variety in the blocks in the landscape, and also making it faster through methods like multi-threading so that it does not end up taking 60% of the frame time budget. There are more far-off goals in the future, such as collision detection and actual polygonal enemies that you can fight in the actual landscape. It's clear that there's a lot of work to be done, but overall I am happy with how it is right now.